This video is about indexing in APL. There are many ways to extract elements from an array in APL. From the beginning, APL had brackets to index specific elements from lists and even higher rank arrays. Later versions included actual primitives functions to do this kind of work. We are going to see both ways. You can start indexing using any number you like. Most languages use 0 or 1 as a starting position, so the index of the first element will be either 0 or 1. But some languages also allow you to specify any number as the first index values. There were some languages that would allow you to start at 1000 if you wished. APL only allows you to use 0 or 1 as starting value. And in these examples, we're only going to be using the value 1, which happens to be the default of all APLs. Indexing using brackets. You can use brackets as in variable followed by bracket and the indices followed by bracket to select any specific element from a variable. The indices don't have to be a single number. They can themselves be a list or even a higher rank array like a matrix. If more than one number is used, they can repeat. Here are a few examples. Variable var contains 20 letters. If we pick the fifth one, we end up with the letter E. You can see using dyadic iota that the letters A, P, and L are in positions 1, 16, and 12. So if we index var with 1, 16, and 12, we end up with the string APL. Likewise, if we index with 1, 16, 16, 12, and 5, we end up with the letters apple. We can replace values in an array by using indices. For example, to replace the third element of a vector by x, we can do var index 3 is assigned the character x. And looking at var, we can see that the third element has indeed been changed to the letter x. The shape of indexing a vector has the same shape as the indices. If we use 3 indices, the result will be 3 values, another vector. If the index is a scalar, the result will also be a scalar. The shape of indexing a matrix has the same shape as all the indices put together. For example, if we use 3 indices for the rows and 5 for the columns, we will end up with a 3 by 5 matrix. To index a matrix, you separate the indices with semicolons. If indices are skipped between semicolons, it is assumed that we mean all the indices. For example, if we index a matrix of 3 rows and 5 columns using only some columns, then all the rows are selected by default. For example, if we have a matrix 3 by 5 of these letters, and we only select columns 2 and 4, APL assumes that we are using every single row, so we end up with a 3 by 2 result. To index a matrix is very similar to indexing a vector. But instead of specifying only one set of indices, you have to specify 2. One for the rows and one for the columns. Here's M. If we only want specific rows, for example 2 and 3, that's the way we do it. If we want only specific columns, for example 4, 2, and 7, this is the way we do it. If we want rows and columns, we put the semicolon between the rows and the columns, and we get the elements desired. The same rule applies to a higher rank array. Here's a 3-dimensional array which has 2 planes of 4 rows and 7 columns. If we wish to select specific planes and rows and columns, we separate them with the semicolon. So here we take the second plane, the second and fourth rows, and the 5 columns specified. Scattered indexing. This allows you to select individual items from a higher rank array. Only some APLs allow you to do that. For example, you may wish to select the element at row 2 column 5 and the element at row 7 column 1. Normally you would have to do variable index 2.5 followed by variable index 7.1. But instead what you can do is say variable, and within brackets you put the indices of each row column pairs. In this case, 2, 5 and 7, 1. The result of scattered indexing has the same shape as the index value, so that if I is the list of indices, then the shape of the result will be the same as the number of elements in I. In some APLs you can use a function called squad to fetch elements from an array. Squad looks like a squished quad, hence its name. The left argument of squad is an array itself, one per dimension of the right argument, to select the elements from it. Effectively, it takes the individual arrays within brackets as left arguments. For example, if array would be indexed by A semicolon B semicolon C, that would be the same as saying A, B, C squad array. You can select a single element from an array and disclose it at once. For example, instead of doing disclose vector index I, you can do immediately I pick vector. I must select a single element. Higher rank arrays can also be used. For example, instead of saying disclose matrix at position I and J, you can do enclose I and J and use that to pick from the matrix. You can even select a single element deep inside an array of arrays. For example, let's say that we have a list of matrices and we want to select the element at row 5 column 7 of the second matrix in this vector. You would normally do first disclose list index 2 to get the second matrix, and from that you would get at row 5 column 7 and disclose that element. Instead, what you can do in one swoop is specify 2 as the second element and 5, 7 as the row columns, and pick directly from the list. Let's see some examples. Okay, here are some other examples. We have an array of 5 elements. Let's find the indices of this array. There are 5 possible indices, 1, 2, 3, 4, and 5, and the third element happens to be a p. So if we check what is the shape of that 3, it's a scalar. It has no shape. So what is the shape of the array at index 3? What is the shape of the result? It is also a scalar, has no shape. If we index with a 1 element vector, we can see that we get a 1 element vector. If we index with 3 elements, we get 3 elements. If we index with 4 elements, we get 4 elements. We can replace some of the elements in the array. For example, at position 2 and 4, we will replace by a space and the letter I. So now when we look at the array, we can see that apple has been changed into a pie. What is the shape of the array? Still 5, hasn't changed. Now let's construct a matrix of 4 by 7. We can see here that it has 28 elements distributed in 4 rows and 7 columns. If we pick 3 of the rows and 4 of the columns, we get another matrix. This time it has 3 rows and 4 columns. 3, 4. If we catenate the 2 sets, 3 and 4, we get the shape of the result. Now in this case here, since we did not specify the rows, we assume we're going to be using them all. There are 4 rows, so we should get a 4 rows by 4 columns, a 4 by 4. And this is viewed this way. The first element of the shape of the matrix is 4. We have 4 rows, and the 4 columns we picked, we end up with a 4 row and 4 column matrix result. Again, if this time we index with a scalar, we get 4 by nothing, so we get a 4 element vector. Because the scalar, the shape of the scalar is nothing. So if we take the first element of the shape of the matrix, which is 4, and we catenate to it nothing, we get 4. So the shape of the result is 4. This is very important because it makes a big difference between having a 4 element result and a 4 by 1 result matrix. The reason for this is because we still have 4 rows, but now we have 1 column. Whereas if we index with a scalar, we don't get a 1 element, we only get nothing. So it's a 4 by nothing. It's a 4 element. But we don't have to index only with scalars and vectors. We can actually index with matrices. For example, if we index the rows with another matrix, which is a 2 by 3, and we index the columns with a 3 by 4, we get a 2 by 3 by 3 by 4. And the reason is because the shape of this matrix is a 2 by 3 and the shape of this matrix is a 3 by 4, which is the shape of the result. So this is consistent whatever you do. Likewise, if we replace the third column, since this is a 4-element array, we have to supply it with 4 values. If we look at that now, you can see that the third column has been indeed replaced with the 4 values that we specified. But if all the values are the same, we don't have to specify 4 values, we can specify only one, a scalar. If we look at it, we can see that the 4th row has been changed with the same value. Function assignment also works. For example, if we want to add 1000 to the second row, all we have to do is say matrix at the second row is plus assign the value 1000, and this will take all the values in the second row, add 1000 to them, and replace them in mat index 2 on this in the second row. If we look at mat now, we can see that the second row has had 1000 added to it. Let's go with higher rank arrays. We'll stick with 3 dimensions. Let's have a look at a 2 by 4 by 7. This is basically the mat that we've added 100 in the first plane and 200 in the second plane. So we now have 2 planes of 4 rows and 7 columns. If we decide to pick the first plane, the second plane, and the third plane, and then use the second row of each one of those, and then the third column, second and fourth column in this, we end up with a 3 by 1 by 4. And again, the rule is the same as we had previously. We had 3 planes, 1 row, 4 columns. So we ended up with 3 by 1 by 4. And we can see again that the shape of these 3 elements, the shape of this element, and the shape of those 4 elements gives you 3, 1, and 4. So the result is predictable. Again here, we are selecting all the planes. We are selecting 1 row, but this time it's a scalar. And then we are selecting 7 columns. So we end up with a 2 planes. The scalar here does not contribute. And then 7. So we end up with a matrix of 2 by 7, shown this way. Again, this time we're selecting 2 planes, all the rows, and this time we index the column with another 3-dimensional array. So we will end up with a 5-dimensional array. And this is seen as the shape of these 2 elements is 2. The shape of this one here is the value of the second dimension of the array. In this case, it is 4. And then here we have the shape of this 3-dimensional array, and we end up with a 2 by 4 by 2 by 1 by 3. Scattered indexing. Here's our mat again. These are all the indices of mat. So we have 1, 1, which is the first element, 1, 2 is the second, 1, 3, 1, 4, 1, 5, and so on, until we end up to the 4th row, 7th column here. If we want to pick the second row, 5th column element, followed by the 4th row, 7th column element, and then the 3rd row, 1st column element, we should have 3 results. If we want to multiply these values by 100, we can do give me all these positions and place them by the same values at these positions, multiply by 100. Now if we look at mat, we can see that these values have indeed been multiplied by 100. Now, we didn't have to use the indices twice. Because we're using the exact same indices, we could have simply said multiply assign by 100. This would have saved us all this typing there. So this is simpler. And if we look at it, we can see that 1 has been added to these positions. 3-dimensional arrays, it is exactly the same thing. In this case, we have to supply 3 indices for each position. This one has got 3 dimensions. We need to supply 3 numbers. 1 for the plane, 1 for the row, and 1 for the column, where we want to value. So now if we want to divide these values by 2, we can simply specify the divide assign 2. And if we look at array again, we can see that at position 1, 2, and 3, the value has been divided by 2. And at 2, 2, 7, it has also been divided by 2. Squad. Here's our array again. What is the third element of this array? It's P. What is array in this index 3? It is P. Technically, we should be enclosing the left argument. But because enclosing a simple scalar doesn't change anything, it is perfectly valid to use this instead of this one here. This is for a vector. Now, if we wanted to have 3 elements, the first, third, and the fifth, then we have to enclose it. And then we get the letters APE, which is the same as this here. Here's a mat. If we want the second and third row, fourth, fifth, and sixth columns, we can do it this way here instead. What is the shape? 2 by 3. We can also reassign these values. Of course, since we have a 2 by 3, we have to supply a 2 by 3 matrix of values to replace in there. Here we have. Here's our 3-dimensional array. Here we have a 2 by 3, so a 2 by 3 matrix, which we can replace by adding 1 to each one of them. If we look at it, all these values have been added 1. Pick. Here's a vector of 3 things. The first thing is a string of 3 characters. The second thing is a scalar, the number 32. And the third thing is mat, the one we were using before. So if we ask for the shape of vect, it's a 3-element vector. If we look at it, we can see that we have ABC on the left, our number 32 in the middle, and the matrix on the right. If we display the shape of each one of the elements of vect, we can see that we have a 3-element vector, a scalar in the middle, and a 4 by 7 as a third element. If we look at the shape of the third element by itself, by disclosing it, we see that it's a 4 by 7. Now, if we wanted to get the 4th row, 7th column of mat, this is the way we would do it. And we get the bottom right element of the matrix. Now, in vec, we don't have mat. We have a separate matrix, which is the third element of vec. And if we wanted to get at that particular element, the bottom right corner, we would have to specify first we want the third element, and in it we want the 4th row and 5th column. And that's it. I hope you've enjoyed this.